see all the familiar names and faces on the screen. I'm a structural geologist, and but I like to do different things, and this is geomorphology mostly, but structural geology is actually an important part of this game. So that's my excuse, I guess. The strandflat is a very important geomorphological feature along the coast of Norway, marked in red in this this map on the upper right. A lot of people live there, farming, fishing, industry, and so on. And it's good to know a little bit about how it formed, of course, and most of you know quite a bit about that. But I'll start exposing what I think I have found out about this strandflat. So we have sort of strandflat-like features many places. It's from the wave-cut platforms from the Bristol Channel, from Denmark, these two pictures here, where you find this near sea level shelf or platform that oftentimes form where you have sedimentary rocks or low-grade metamorphic rocks that are easy to erode, even sediments here in Denmark in the Danish case. And that's what people think of, I guess, first when they think about the near sea level sort of platform along the coast. When the Norwegian case is different. It's carved out in hard metamorphic and magmatic rocks, and it's very wide. These wave-cut platforms that we find many places are usually tens or hundreds of meters at the most. The strandflat that we have in Norway is tens of kilometers wide in places, and that's a huge difference. It's also very irregular. It doesn't, you know, this is, we can see there's a escarpment here in the back, a cliff, a little bit curved, but there's only one cliff, and then there is the platform on the ocean side. That's very different from what we have in Norway, where we have sort of islands of sort of rest mountains that were not planized or not flattened by erosion. So it's not a straight line. It's a very, very curved and complicated in detail eastern limit of this strandflat that we have. And it occurs in a region of very strong recent glacial erosion. So that's also an important point, with repeated glaciations, as we know, over the last 2.5 million years or so. So in this presentation, I'm going to just talk a little bit about the strandflat, the way I have observed it in West Norway. That's my focus area, and how it formed and when it formed, like the processes. So there's one suggestion here in the picture, which I don't think is so viable, but okay. So we're talking 130 years of discussion around this strandflat problem, how it formed. And it all started with Hans Roisch in 130 years or so ago, and he did a nice piece of work. He was into wave erosion mostly. Then came Fridtjof Nansen with some very nice work that, and I think he got most of it right at that time, more than 100 years ago. And then came father and son Oltedal with some very more extensive, very, very, very nice works on the strandflat. And then there's a lot of other people. Some of them are mentioned here. And the last two contributions is by Helge Løseth, who I actually think is online here, and myself. And the interesting thing is that we did this completely independent of each other. Helge did a longer stretch, mostly the whole strandflat. I focused on West Norway and more details located there. But we came up with pretty much the same conclusion, which is an interesting thing. Okay, the strandflat. In the old days, observations was mostly made from what we could see on shore, what's above sea level. Today, we also have good bathymetric data, and we have seismic data. In particular, this area here is very well covered by very good seismic data, high quality seismic data, 3D data that allows us, and it goes all the way into the strandflat area, which is marked in green, allows us to connect the strandflat to the North Sea Rift Basin. So we have the onshore, we have the shallow ocean, shallow sea part from the bathymetric data, and the offshore that we can put together in a map like the one that is shown on the right. So the strandflat here is this sort of light, or here, sort of the light gray blue color here. That's the strandflat. We look at this from the southwest, it will look something like this, the seismic data offshore. And now we have removed all the sedimentary layers and rocks offshore, and we're looking at the same surface, not exactly the same surface, but the top crystalline basement surface onshore. And the strandflat is here, the stretch here, and then we get offshore and see the west dipping top crystalline basement surface there. These surfaces have different ages, different parts of this area, but it's the top basement is a natural thing to connect offshore and onshore. These pictures are just from wells showing the basement very similar to the onshore basement. That's so important here. Okay, so if we look at the strandflat to the east, there is usually a steep cliff like we had in the wave cut platforms. There is a steep cliff, but that cliff is not linear. It curves, and we find it many places on the back here, actually, on the back here and here, and it's very irregular, like we already mentioned. It's very steep. In this case, this is up here in the North Fjord area, Vemorland, and the whole strandflat, most of the strandflat is actually submerged in that part. So we only got a very good view of this recently from the bathymetric data. We'll get back to that area. In the west, and this is a topographic model. So there's the escarpment in the east cliff. There's the strandflat. And then in the west, as we get far enough offshore, we start to see a west dipping surface. The top basement is west dipping. So and it's a fairly sudden break between the horizontal, sub-horizontal strandflat and the west dipping top basement offshore. So that's characteristic. Then we have the whole perspective of the strandflat. It's near sea level. It's a little bit below sea level up here in the north. It's above sea level, mostly in the south. Sea level is not shown on this map. It's what is shown in this color is an interval from plus 75 meters, so 75 meters above sea level, current sea level, and minus 150 to cover the whole stretch. And it's an area of, we can do objective analysis of this in terms of roughness. If we do a roughness analysis, this red warm colors indicate low roughness, so a fairly smooth landscape, and that is coincident more or less with the strandflat area. Right. Now we can look at the slope, the dip, the one. slope of the surface. I think this was made by 250 by 250 cell size. And you can see the warm colors again, very low slope. Oops, very low slope, very horizontal. So that's sort of an objective analysis of the strand flats. And processes. How did it form? So Royce, for example, he was arguing for a wave cut platform kind of model, and he thought that would take a long time. So maybe we have to include not only the quaternary period, but also time before the quaternary to make that. So wave cut. That, I don't think that's very important. Then we have processes related to quaternary glaciations, so cirque glaciers, frost shattering, and sea ice erosion, this kind of stuff. And Nansen was arguing for that, in favor of that, and also Holtedal, Larsen and Holtedal. I don't think that's a very important set of processes. And some people think that the Mesozoic landscape or the Mesozoic surface, like Triassic, Jurassic surface, was buried and then re-exposed, and that's what the strand flat is, more or less, at least to some degree. And I don't think that's overall the case. I think the strand flat formed independent of that surface. Let's see. Okay. So when I think strand flat and I look around, I see these mountains sort of, this is Eldsfjell north of Bergen, sticking up, and then there's the strand flat close to sea level. And I see in some places they are smaller. This is Olden. The strand flat is around sea level here, little mountain here too. And this, in this case here, we have just small remnants of these rocks that I think. So I think this is like progressive evolution, and I think these were being attacked from all sides, same time more or less, and that helps explain why the strand flat is so wide. We get back to that actually here. So in some areas we can see the strand flat, what seems to be the strand flat, being very limited, and we have these big patches of higher land. And then in other places we see that these highs are smaller. The strand flats, the strand flat gets bigger. And in other places we can see that it's mainly the strand flat, just some small patches of higher topographic features, mainly the strand flat. So I think this is like a progressive evolution of strand flat formation. And through this, I mean, you have erosion processes going on in many places at the same time. And then you end up with something like a garden, for example, that's up here. So, a garden, very flat. There's no sort of mountains left or big hills left. Not completely horizontal. It's not completely horizontal, but it's relatively, on average, pretty horizontal. What we also can see here is these kind of sounds, is erosional lows here, small sounds and things. These are caused by faults and fracture sounds, and those I think are important in this context. I think this, if you believe aerial photograph observations, it seems like faults and fractures increase in numbers from the east towards the coast onshore. So that makes it easier for the strand flat to form along the coast, because you have a lot of fractures, more than normal in this country. So that's important. So once you have fractures at different scales, it's much easier to pick off pieces of rock, and I think that's important. I don't have time for this, but I will go to this. So there's actually some nice evidence of cirque erosion in this area. The Bergen is down here. This is Australia. Transfuel, and this area here, we can see evidence of that being preserved. And cirques could, if they occur along the coast, they could erode down to more or less sea level and add to the strandflat. So there is evidence for that process too, but I don't think it's very important overall, but it is a factor to be considered. What is more important is probably frost weathering, as we mentioned, maybe the most important process. And certainly more important than wave erosion. Why is it more important than wave erosion? Because we see erosion going on all sides of these rest mountains. So they are attacked from all sides, not more from the west where the waves will come in from the west more, but everywhere. There's no clear favoring the west side of in terms of erosion. So it's not wave erosion that is the most important. Cirque erosion and sea ice erosion, I'm more uncertain about. That's the importance of that sea ice sort of freezing onto the rock and then tearing off pieces of rock as the ocean moves the waves and everything. But okay. So frost weathering, so that happened when the climate was colder than today in general, but not during the glacial peaks, because then you had big glaciers covering the whole coastal area, at least at the very peak. But in periods when it was colder than today, but there was no glacier covering the coastal area completely. So this points, of course, to Quaternary age. And it's consistent with the strandflat cutting into pre-Quaternary surfaces, as we can see on this profile, for example. This is a profile across southern Norway. Jotunheimen would be here, the high mountains there. Then we get to the coast. Well, that's here. And then we get offshore, and that's the offshore sedimentary basin here. And the strandflat, it's not so big on this large, long section, but it's cut straight into this Jurassic surface here, for example, and even the younger surfaces, tertiary surfaces. So it's definitely a superimposed surface, cutting the offshore layers, pre-Quaternary layers, and also cutting into what's called the paleic surface. The surface that people have been talking about for a long time, that you can see if you connect all the oftentimes sort of flat peaks or highlands of the country, and you can draw a surface like this. It cuts into that too. And that's probably a surface that was as close to the surface that was there before the Quaternary at the end of the Neogene. And that's the surface that you see here, for example, top here. In the west, it's pretty low, and then it gets higher. So that will be this right there is that. And it gets higher inlands. So again, the strandflat, very horizontal, cutting through everything. Has to be young, certainly younger than the Jurassic. You make profiles across the coast, all the way from the north to the south, from Conway to Stutz up here. You see that this surface is always dipping. This Jurassic surface is always dipping and cut by the strandflat. A little bit more, some places. Bemlu, for example, strandflat is very horizontal. The Jurassic is dipping, even though the angle is not as big there. It's very clear all the way everywhere. So it's definitely younger than Jurassic, and very likely Quaternary. Back to this one, we see the same thing. Again, strandflat, slightly dipping to the west, not much. And then the Jurassic top basement surface like this. So this is a stratigraphy offshore with the mid-Jurassic, upper Jurassic like this. So this here is the surface, more or less like this. We're looking at above here. So that surface projects above the strandflat. How far above is difficult to say, but we have thermochronological data that indicate that it may be 1 or 2 kilometers in this position here. This is something we're working on, trying to constrain that. And then a younger surface is the paleic surface, probably Neogene. That's at least more or less. So definitely a young structure. And Nansen showed this also very, very well, that it's actually fairly horizontal in some parts of strandflat. It's very little, like 20 meters above sea level here in Garden to 40 meters above sea level far in here, several tens of kilometers to the east. It's surprisingly horizontal actually in some places, because this surface has to be, it must have been formed sort of repeatedly during this repeated ice age history of ice ages, right? So you had the right climate and the ice came and covered everything, and you got the right climate again. So then it started over again. But it managed to end up with a fairly horizontal surface in many cases. Of course, broken up by faults and some fjords and things, but that's natural. If we look at the north-south section, it's higher in the south than in the north. Here is the south, Karmøy, 40-45 meters here. And then it dips down to below sea level up here by its dots. This is where we looked at one of the first pictures. And that's because it crosses the isobases. It crosses these curves that tell us how much uplift there was during the post-glacial rebound, isostatic rebound after younger dries. And it takes us from 30-40 meters in the south, that's what we have more or less, up to there's the zero is lines here, so it's negative 10 or 20 meters in the north. So it fits actually pretty well. So the differential isostatic readjustment has modified the strandflat and tilted it to the north. And in the end, like, let me summarize with this figure here. This, like, the way I portrayed this, I imagined this when I did this a couple of years ago, 3 years ago, that at the start of the Pleistocene glaciations, we had a landscape, a pre-glacial landscape, everybody agrees on that, and it probably was close to the peaks of many of the mountains that we have. And you may have had some degradation of the Jurassic nonconformity offshore, right there. But in general, we have these two surfaces. And then climate got colder. We started to have frost weathering and other glacial or cold environment processes. And this is where fractures and faults are important, because this is where we had already some valleys, I guess, and then we started the processes on each side of this fault controlled valleys. And again, the processes were going on many places at the same time. Not exactly the same time, and it worked its way eastwards, I guess, but in general, it's not like it started in the west, working its way to the east progressively. It was working in many places at the same time, must have been. And then we have the glacier advancing from time to time. Everything was covered by a big glacier, and I'm sure it picked up things and worked and added to the flattening of this landscape. But then it retreats, and you're back to at least in periods of climate that favors frost weathering again, so it picks up the work again. And this happens probably over and over and over again. I don't know how many cycles there would be, for 40 or something. And what we have today is the result of this cyclic sort of erosional history with strand flats and some leftover mountains in between. And that's sort of my interpretation of this. So by that, I think I will stop. So thank you for your attention.